Thank you. So let me introduce the speaker. Professor Srikanth Patala is a faculty in the Department of Material Science and Engineering at North Carolina State University. He is currently working on a wide range of topics with an intention of developing novel materials, metallic and ceramic materials. So they use a combination of both analytical techniques and computational simulations in order to um, develop an understanding of these materials. So today he will be talking about computational tools for high throughput exploration of the interface genome. Over to you, Dr. Srikanth Patala.
Okay, thank you. Thank you for the kind introduction, and also thank you for the invitation, Professor Anand and Professor Ratna. I just want to quickly mention the funding sources here, both from Air Force and National Science Foundation, and one of my group members, Leila Khalili, who was basically instrumental in most of the work that I'll present today. So most of actually my research focuses on understanding the interfaces from an atomistic perspective. This will be a deviation from the previous talks where the analysis was more using phase field techniques, I would say maybe at the mesoscale or at the macro scales. We are really interested in the atomistic length scales. I want to first provide brief motivation here. Interfaces show up in many of these higher length scale simulations, and we use certain estimated or approximate properties for these interfaces. Interfaces are basically defects that are present in most engineering materials, which tend to be polycrystalline. These are, these are basically two-dimensional defects that occur within polycrystalline materials. As an example here, illustration of a brass copper alloy, or in ceramics where abnormal grain growth is shown, in alumina where the interfacial properties actually drive abnormal grain growth, and even in minerals there's a lot of interest in texture and understanding the role of interfaces and geological phenomena. So again, as motivation, polycrystalline materials occur in most engineering applications. Turbine engines actually is one of the examples where single crystal materials take precedence, but there are also components there which are polycrystalline. At high temperature, interfaces dominate the properties. For example, the creep properties tend to be grain boundary dominated, the grain boundary diffusion dominated. And one can envision changing the chemistry due to the thermodynamic interactions at the interfaces to really enhance the properties of the material without changing the core chemistry of the alloy itself. What we are interested in my group is what's referred to as anisotropy, which is the variation of the property of the interface in the same material. For example, here I'm just showing as an example of high purity copper. So this is basically a copper system, and showing a property that's called a sink efficiency. So these materials, let's say we want to use for cladding materials in nuclear reactors, when they're irradiated, the interfaces absorb some of the defects that are produced within the material. And one can measure what's called as a void denuded zone width. This lambda is a proxy for how effective the interface is in absorbing the defects. So when you have a polycrystalline material as such shown here, I can zoom in and measure this lambda, the width, for different interfaces. And what I mean by different interfaces is actually governed by crystallography. So very quickly, what is the crystallography of an interface? There are actually, we call this a 5-dimensional space for those of you who are familiar. There are two important parameters here. One is the what's called as a misorientation between the grains. So crystals, you can define a reference coordinate for each grain. The difference in the orientation or the rotation between the two crystals is referred to as the misorientation. And then I have the boundary plane, which, for example, it can be 1, 0, 0, 1, 1, 1, 1, 1, 0. So this can be defined by a unit vector. So there are in total 5 unique crystallographic parameters that define the crystallography and hence the structure and properties of interfaces. If we were to now project it into a lower dimension, and if I were to plot, as an example, the sink efficiency or the void-Newton zone width as a function of the inclination angle. Inclination angle here is the angle that the boundary plane makes with the misorientation axis. You see there is a variation, which is basically refers to the anisotropy. For a very specific set of boundaries called sigma 3, I'll talk about what sigma is actually in the next few slides. Or if I were to project it to a misorientation angle, you see a lot of scatter here in terms of properties, basically saying that a property such as sink efficiency cannot be projected down to these smaller dimensions to understand the variation of this property as a function of crystallography. So this is another aspect that we're very interested in my group, basically understanding the properties of interfaces to better design novel materials. So what I'll talk about today is this vision that we have in providing and also having a framework for simulating interfaces so that we can generate databases of interface properties that one can use in higher length scale simulations for materials design. Again, to motivate, I just have a summary of I would say more recent, let's say in the past couple of decades, a collection of various properties of interfaces that have been measured, specifically grain boundaries. Energy is a very common property that is measured, which we can correlate to microstructure evolution. Mobility is another slightly more complex property that can be, measured experimentally and using simulations as well. And then, again, correlating to the kinetic properties, diffusivity, and correlating to thermodynamic stability, which is segregation thermodynamics. Generally speaking, it's easier to simulate these properties than to measure experimentally. Generally speaking, the simulated properties tend to be not as high fidelity, so they're more approximate, but simulations do tend to give you trends for the properties that one can use for either higher length scale simulations or better understand the thermodynamic and kinetic properties of the materials. So as I mentioned, we want to develop such databases for specifically interfaces. And just to put this vision in context, in terms of this idea of developing data-driven design of materials, there are somewhat established databases, especially using density functional theory methods. These are 3 examples, probably most common out here in United States Materials Project, AFlow, and OQMD. And these tend to be single crystal properties. Really, if we want to, especially in structural materials side, if we want to design materials, we have to move towards defect properties. And a couple of examples here. There is a database for grain boundaries, which in the grain boundary community, we refer to as Olmsted's database. There are about 388 grain boundaries of 4 FCC metals. And more recently, about 327 grain boundaries of total of about 58 elemental metals. But again, in a 5-dimensional space, about 300 boundaries, 400 boundaries is actually very sparse sampling. And what we want to do is really explore this 5-dimensional crystallographic space for different material systems, both as simple as cubic, but also more complex material systems, and also move towards more complexity in terms of alloying elements. So we have developed a couple of tools, mostly Python-based. BiCrystal has what I call as bicrystallographic properties of interfaces, and GBPy, which basically has these wrappers for lamps, which is an atomistic simulation tools to automatically simulate these interfaces. All right, so again, very quickly, just going through the vision of this project. We want to combine or take the experimental studies that have been done on interface grain boundary properties, combine it with atomistic simulations. And to do so, we need these high throughput computational tools. And once we have these databases, we would also like to have some statistical capabilities to analyze or predict properties more generally for interfaces. I'll just mention here, GBPy is a Python package. It's actually open source, available on my GitHub repository. I provided the link for it in the abstract, where we are curating these tools for simulating grain boundaries in general. So from now on, I'll go over some of the challenges that we've addressed for facilitating these tools, and I'll give a more big picture understanding of what the algorithms do. I will provide references, and I'm happy to take questions as well if you want to go into more details, but I do want to cover quite a bit of material here just to make this talk comprehensive. So if you have more questions, I'm happy to take those if you want to go into more detail. So specifically 3 challenges we wanted to address. How do we generate these grain boundary structures more efficiently as compared to traditional brute force techniques? How do we generate grain boundary structures for low symmetry systems? And there we have to generate an input structure where we need to know something about the crystallography of the interfaces. And finally, how do we perform statistical analysis in this 5-dimensional space of grain boundaries? So very quickly, in terms of the atomistic simulation itself, the traditional way of performing grain boundary simulation is you construct what's called as a bicrystal. So you take 2 grains, 2 crystals, have them misoriented, give them a specific misorientation and a boundary plane orientation, and then we do these what are called as microscopic changes to the structure. We relatively translate one crystal with respect to the other. We move the boundary plane within the crystals. We also change the number of atoms right at the grain boundary. So that's the grain boundary density in terms of atoms. And this is usually how it's done. Traditional technique tends to be very slow, requires a lot of initial structures to get to a grain boundary configuration that has a low energy structure that can be used for further simulations. So very recently we developed, and it's summarized in this paper out here, and we're actually currently right now preparing a tutorial article, a hybrid Monte Carlo molecular dynamics technique. And the Monte Carlo procedure basically involves perturbing the structure, and really the art here is how do we get good perturbations that will lead to low energy structures. And we identified 2 perturbations which are quite simple here. We remove either a single atom from the grain boundary, and we remove it stochastically. So higher the energy of the atom, more likely it is to remove that atom from the grain boundary. We also insert atoms, and this actually has, we realized is a very important step because the insertion, if you don't have insertion, the removal actually starts to cause voids within the grain boundaries and gives pretty unphysical structure. So the combination of this atom removal and insertion is what gives you this Monte Carlo scheme that results in very fast convergence to these grain boundary, low energy grain boundary structures. And the insertion also is a very geometric algorithm. We identify voids within the grain boundary structure using a Delaunay triangulation type technique. And the voids here are shown, and we insert atoms specifically at these voids because it's an off-lattice technique. So a priori, we are not sure where to insert the atoms, so this geometric algorithm helps us inform where to insert the atoms. All right, so as I mentioned, I'll give a very big, big picture summary of these techniques. So I'm going to move on to another important challenge for simulating grain boundaries in low symmetry systems. So how do we generate this initial configuration that's periodic? And the motivation is low symmetry crystal systems, for example, hexagonal materials like magnesium or even monoclinic zirconium. Zirconia is another material system that we're interested in my group. And also for what I call as heterophase interfaces, where there is a certain orientation relationship between the precipitate and a matrix that's of interest. And these orientation relationships lead to low energy interfaces. But again, a priori, we're not sure what these low energy orientations are unless we have some experimental results to guide what that simulation, what that specific orientation relationship should be. So, you know, for classic systems, for example, in martensitic systems, there is Bain orientation relationships. But again, if we want to do a high throughput type and exploration of interface structures, we need to be able to predict what orientation relationships might be important. So at these low energy orientation interfaces, we have what is called as good geometric matching. So if you were to overlap two crystals on top of each other, you have these matching sites. And then between these matching sites, you have certain distortion. Okay, so that's kind of the geometric criterion which drove this algorithm that I'm going to present. So this is the algorithm for generating what are called as coincident site lattices. So in this example, these sites where I have the coincidence between the parent and the product phases, those are coincident sites. Similar coincident sites exist for grain boundaries as well. So the challenge here is how do I generate these coincident site lattices for an arbitrary Bravais lattice? There are algorithms for high symmetry systems, for example, cubic. There are algorithms, but for arbitrary Bravais lattices, this is pretty complex. And for any given degree of coincidence, the sigma here gives you the degree of coincidence between the two lattices. Right? So let me quickly show an example if you're not aware what a CSL lattice is using this two-dimensional hexagonal lattice. All right. So if I have two, we create an interface with two grains, right? So if I have two lattices, I'm just using a hexagonal lattice as an example with certain misorientation. What we do is we overlap them on top of each other. And if you look very carefully, there is a coincident site lattice. So there are atoms that are coincidence on top of each other. And that lattice is what we are interested in. And what is this misorientation that gives me that coincident site lattice? I guess that is the more important question here. So how do we generate these misorientations that give me these coincident site lattices? And how can we do it in an automated fashion? All right, so this work again, we just recently submitted to Journal of Applied Crystallography. So the technique here is to generate what are called as Hermite normal forms, and these are basically giving us what are called as sublattices, but they're giving us unique sublattices. So if I have, let's say, again, I'm going to use the square lattice for illustration, but it can be used for any general lattice. So suppose I have a square 2D lattice and I'm interested in generating all the sublattices within this square lattice that are 5 times the area of the primitive lattice. All right, so that's where the sigma number comes in. Okay, so that can be done using the simple algorithm. There are actually 6 unique sublattices, which are called as Hermite normal forms. Those of you who are familiar with density functional theory, Hermite normal forms are actually used for generating what are called as derivative structures. So the idea is as follows. So once I have these, let's say, sublattices of area 5 times the area of the primitive lattice, I'm going to compare these unique sublattices. Compare meaning, is there a rotation that can map one of these lattices to the other? And you can already see how see some of these sublattices. If I rotate this by 90 degrees, I get the other sublattice here, right? So I'm going to show that here. So if I were to rotate the blue sublattice here by 90 degrees, I should get the red sublattice. But remember, 90 degrees is actually a symmetry of the underlying crystal, so this actually does not generate a coincident site lattice. One of the examples here, that's actually these two sublattices. The rotation is about 37 degrees or so, which gives me a sigma 5 misorientation. Okay? So this identifying sublattices and identifying orientation relationships automatically gives me these coincident site misorientations. The challenge with low symmetry systems is, as I showed in one of the examples, the coincidence is not exact. I have to distort the lattices by a small amount to get coincidence, exact coincidence. So to address that challenge, we actually developed a technique called as point pattern matching, and this is more common in, I would say, computer science literature and computer vision type fields, where let's suppose I'm interested in identifying this some pattern. Let's suppose I'm just again using a 2D example here. Suppose I'm interested in identifying a pattern that's shown here in this larger set of atoms. This point pattern matching algorithm, again, if you're interested, please refer to this paper, identifies those set of atoms if they exist, even if they are slightly distorted. So they don't have to be an exact match. So we can use that point pattern matching to actually compare sublattices that are slightly distorted with respect to each other. This is what happens in low symmetry crystal systems. So again, here shown are examples of sigma equal to 5 type coincidence, but I've distorted this square lattice by a small amount to basically show that if we were to do a general comparison, I would not identify a rotation that can map one lattice to the other. To identify, to use this point pattern matching algorithm, we first actually generate a small pattern within one of the sublattices by taking an environment within a cutoff radius, and a larger pattern within the other lattice, which we call the target. So I slightly increase the cutoff, and then I take another pattern. Now I can compare these two patterns to get the orientation matching. So this is actually similar to, the coincident site lattice in dissimilar materials, such as a precipitate and a matrix, or in low symmetry systems. So as you can see here, the mapping is not perfect. There is a distortion between the two lattices, but we can use the point pattern matching technique to identify this mapping. We can also, the point pattern matching actually also gives me a strain tensor. So this gives me the amount of distortion that I need to apply to get the perfect matching between the two lattices. And all of this, again, is automated. All I need to ask this algorithm is, can I generate a coincident site lattice with, in this case, the coincidence number being 5, which is basically the area of the sublattice with respect to the primitive lattice. So quick summary of this technique. For any given arbitrary Bravais lattice, so any low symmetry system, and a given coincidence site number, we can generate these unique sublattices using the Hermite normal forms and compute the transformation between any pairs of sublattices using this point pattern matching technique. So this point pattern matching technique now allows us to identify these orientation relationships that are important in material systems, and also gives a strain associated to result in perfect matching. So this technique we are now using to generate grain boundaries in an automated manner for hexagonal crystal systems. But as I mentioned, the application goal is for general low symmetry crystal systems. Okay, so again, going back to this vision that we had, another topic that I want to touch upon very quickly is, once we have these databases, once we are able to either experimentally generate properties of grain boundaries, or from a simulation perspective, simulate the properties of grain boundaries in this 5-dimensional space, how do we perform statistical analysis? This is basically how do we fit curves in this 5-dimensional space for prediction. Right? And one of the reasons we have to go to slightly complex techniques here, and when I say complex, actually these techniques are pretty standard in, I would say, let's say data science driven methods. But these have to be now transferred to our material science specific problem here, where we have symmetries, right? All my crystals have underlying symmetries. So if I have a measured property, I want to make sure that the symmetrically equivalent instance of the grain boundary also has the same property. So I'll quickly show here what we developed is what's called as a kernel function with symmetries. So as an example, if I have 2 points, what a kernel function measures is the similarity between those 2 points. So in some sense, it's giving me the distance between the 2 points. If the 2 points are very close to each other, the kernel function takes a large value, let's say 1. If they're far away from each other, the kernel function decays to 0. And why is that helpful? Basically, in many of these statistical techniques, the kernel function is used to do the interpolation. So if 2 points are close to each other, their properties should be similar. And if they're far away from each other, their properties do not have any correlations. So we can build this information into using what's called as a kernel function. But the challenge here is using symmetry. So as an example, if I have, let's say, this yellow point here, and I want to measure the distance to this white point, to consider all the symmetrically equivalent points. So if I were to move the white point farther away, then one of the yellow points, let's say here, the symmetrically equivalent one will become closer to the white point. So I have to make sure that I consider all the symmetries. So what we do to develop this kernel function is actually using what are called as basis functions. And to quickly introduce that problem, I'm going to again use a 2D example. Right? So let's suppose I have a parameter theta with a twofold symmetry, which means that instead of 0 to 2 pi being the domain, 0 to pi is the domain of interest, and pi to 2 pi is symmetrically equivalent to 0 to 2 pi. Okay? If I were to define a distance metric using which one can define a kernel, the distance metric will be minimum if I have theta 1 and theta 2, minimum of theta 1 minus theta 2. But because of the twofold symmetry, I have another distance which is pi minus theta 1 minus theta 2, and I have to take the minimum of these two. This is where symmetry complicates how we compute distance between any two parameters. An alternate approach, actually, which is what we proposed in developing this kernel for spaces that have underlying symmetries, is one can use the basis functions. For example, Fourier series are the basis functions for defining any function on a circle. Right? So if I have a parameter theta, I can use, and I have some function of f of theta, I can use Fourier series expansion to define a function on this circle. If I have 2 pi periodicity, then I can ensure that I take basis functions that satisfy that symmetry by basically only considering even numbered coefficients within the basis functions. And what we do is then define a delta function using the Fourier series. So this is, for example, shown here as a delta function that's built using the Fourier series basis functions. So what we use is the coefficients of this basis function as the descriptor, which already has the symmetry built into it. As you can see, the delta function has a peak not only at 0, it has a peak at minus pi and pi as well, because we are only using even numbered coefficients, which has pi periodicity. And using a property of these basis functions, I can define a kernel, which is basically an inner product of the coefficients. So if I have the coefficients expansion at theta 1, and if I have a coefficient expansion at theta 2, I have two sets of coefficient. The inner product gives me a kernel. So these coefficients is the feature vector, and I can define a kernel. For example, if I want to define a similarity between theta equal to 0 and any other theta prime, all I have to do is a dot product between the coefficients. And again, it basically, the kernel looks like the delta function, and that's the idea here. So if I have a theta that's close to 0, then I take a high value. If I have a theta that's farther away from 0, it's a low value. Again, when I go close to pi, I have a high value again. So that's basically giving me this. Sorry?
घरी रेंज नाही ना.
All right.
I think somebody is having their mic on. Could you please switch it off?
तिला आज नाही केला, तिला काल बंद होता ना फोन.
Yeah, I think we have someone with their mic on.
I just switched.
Okay.
Yeah. Sorry about that. Yeah.
No worries. All right. So one other slight modification here. Again, if you're interested in the properties of a kernel, these fluctuations are not very good. So we can smoothen those fluctuations by what are called as Rees factors, and this is again very common in expanding basis functions for functions that change very quickly, for example, as a step function. So we can apply these Rees factors, and that's what is smoothing out the function here. As you can see, if I change these, the order of the Rees factor, I can go from this somewhat fluctuating delta function to more smoother and smoother delta function. So this is basically our kernel, which has the symmetries. Now that I've, so when we have a kernel, we can also define a metric. That's basically given by this function. This is one of the functions that you can use. There are many other functions as well. To show that my metric is working, or my kernel actually makes sense, I can plot it with the metric that I initially defined for this twofold symmetry system. So on the x-axis is a metric between any two thetas, using what we can call a canonical metric, or a metric that basically is obvious and makes sense for us, versus the metric that I defined using this new kernel. And you can see there's one-to-one correspondence. Of course, it is not a perfect straight line because this is a mapping. But the one-to-one correspondence and a monotonous function here basically gives you confidence that this is a kernel that one can use for statistical analysis. Now, of course, this is a simple example in 2D for, let's say 2D crystals with symmetries. How do we extend this to real crystal systems or even grain boundaries? As long as we have basis functions, we can extend this, and basis functions that can be symmetrized. Specifically for, let's say, crystal orientations, I talked about, if I have theta as a parameter that defines a crystal orientation in 2D crystals, I can use Fourier series as basis functions. If I have two parameters, let's say for a unit vector, one can use spherical harmonics. These are basis functions that are used to build functions on a sphere. For crystal orientations, these are basically rotations. These can be parameterized using what are called as quaternions. I won't go into the details here, but the main point being we can use basis functions which are called as hyperspherical harmonics. These are basically extensions of Fourier series to 4 dimensions. Okay. So these basis functions can also be symmetrized. For example, if I have crystals with octahedral point group symmetry, I can symmetrize them, and that actually symmetrization is provided in this paper by a colleague of mine, Jeremy Mason. We've extended this to actually grain boundary crystallography as well, and that is the idea here, to get to grain boundaries. So when we have these symmetrized basis functions, we can use the coefficients as the descriptors for crystal orientations such that the symmetry is already built into the system. That is the idea. So
we have about 2 more minutes.
Yeah, I'm concluding soon.
Thank you.
So just as an example, to show in the orientation space, we can again define a distance or a metric using the basis functions, and a distance using quaternions along with the symmetries. And I'm plotting here. Again, you see a nice one-to-one correspondence at low distances. At high distances, of course, there's a spread here again because of the mapping, but really this one-to-one correspondence at low distances and a monotonous relation, again, should give you confidence that I can use these basis functions as descriptors for my orientations. As an example, if I were to use this quaternion metric with crystal symmetries, it takes about or as compared to the basis function metric that I defined here, it's about 3 orders of magnitude faster just using the basis functions because the crystal symmetries are already built into the basis functions. All right, so just want to conclude quickly so that we have time for questions. I wanted to introduce this software package that we're putting together, a set of tools for grain boundary simulations. I briefly talked about high throughput interface structure generation using Monte Carlo molecular dynamics technique. We've built tools for generating these input structures in low symmetry systems in this package called Bicrystal, which is actually a part of GBPy, basically using the point pattern matching technique. And those input structures are used for simulating, that can be, are used as input for this high throughput interface structure generation algorithm. And finally, when we have these properties that are curated, how do we use statistical analysis? I introduce a kernel or a way to define distances in the space with symmetries. And really incorporating the symmetries is the key here, and doing it in a manner where we can actually perform statistical analysis. And kernels are basically the fundamental idea here. Kernels are used in, for example, Gaussian process regressions or even in support vector machines for performing any type of statistical analysis on the property side of things. So with that, I'll conclude. These are all, just want to give you a quick overview of students and postdocs in my group who have contributed to different aspects of the project, but Leila, who is the main student who has performed most of the work that I presented today. All right, that's it for me. I'll take any questions.
Thank you very much. That was a very nice talk. So we have some time for questions. So there is one question from Veera S. Slide 44. Can a nonlinear kernel be developed that can give one-to-one correspondence? You can think of using a nonlinear kernel as in kernel SVMs.
Yes, so actually, I hope I understand your question correctly here. The kernel that we have here, as an example, let me show this plot here. It takes a high value when you're basically close to the point and then goes back to 0. And we can adjust the width of the kernel by changing the Rees factor summation here. So you can think of this as a Gaussian kernel, right? Or a radial basis function kernel, that if you're familiar with that. So if I were to put a Gaussian function at a point, it'll take a high value at that point and then will decay to 0. And using radial basis functions, you can build any nonlinear function. So similar idea applies here.
George, I would like to ask a question. Could you please unmute and ask the question, Mr. George?
Yeah. Am I audible?
Yes.
Yes.
Okay. Not very specific to specific topic here, but just a general question for the people who are not exposed to the computational materials, integrated computational materials. What are the prerequisite you will suggest, sir, to start with? Whether you should be start with statistical and mathematical this thing to enter into this field and to upskill himself. Where do you see for the professionals who are in the very core team, who are doing the physical metallurgy and core physical testing and other things, want to get exposed to this and to upskill this computational materials? Where do you think
Okay.
where they start?
Yeah. Excellent question, probably broad and applicable to all the panelists here, but I can give you my couple of concepts that I found useful. If you're, from your question, I felt like maybe it could be more industry relevant. And if so, actually, CalFAD and, kind of getting a good basis of thermodynamics is a very good place to start.
Okay.
And, CalFAD and understanding phase diagrams and how to use them for materials design has been has gotten a lot of traction in industry. But if you want to move further and perform more specific material specific simulations, it depends on what length scales you're interested in, right? So some of the talks have focused on phase field, or if in mechanics, the finite
the
element
microstructure
techniques.
evolution specifically to have the
Yeah,
on the
right.
product performance correlation with property microstructure.
Right. So at that level, definitely, the finite element type techniques and phase field techniques are probably the most used in industry and, of course, in research as well. The atomistic side of things, I would say, I tend to think of it as being a bit more fundamental, but are important to inform those higher length scale simulations. So, we use specific properties. If I'm interested in microstructure, grain growth as an example, I have some estimate of what is the grain boundary energy. But in reality, it's a much more complex function, as I hope I've conveyed here. So atomistic techniques tend to be more relevant for understanding trends at the atomistic length scale. Just a quick comment, I guess I'm sure there are talks on density functional theory technique as well. Those are also used, again, in research and industry, but they tend to be, limited to how many atoms that you can simulate, of the order of hundreds, let's say. So the type of systems that you can simulate is limited. So these are, I would say, different length scale simulation techniques, and depending upon your specific interests, there are definitely different courses or different techniques that one should pick up. Yeah.
Thanks,
Thank
thanks a
you.
Hope
lot,
that
sir.
answers your question, and I'm
Yes,
sure
yes.
other panelists have more insights into this as
Yeah.
well.
There's
Thank
another
you.
question from Bira S, and it's how does your method for grain boundary generation compare to genetic algorithm or particle swarm techniques?
Right. Good question. And, we didn't really compare in terms of efficiency, but let me quickly try and see if I can go to the technique itself. So Monte Carlo, is, I would say, has more of a history. And one of the advantages that I've found is it's easier to extend if I'm interested in getting functions like free energy. So of course, I talked here only about how do I generate a lowest energy structure, and genetic algorithms or other techniques can also be used. What we have used here is actually a very specific perturbation technique that can be incorporated in genetic algorithms too, in fact. But one advantage, and one of the reasons I wanted to go with Monte Carlo, is there are extensions of Monte Carlo that can help you, for example, do ensemble specific simulations. For example, if I'm interested in a grand canonical ensemble, right, and I want to know what the free energy of the interface is, it's more obvious how to do it in Monte Carlo. You can do it in genetic algorithms too, but it's much more complex how to set that up. So just given its historical context, the technique is much more well developed for generating ensemble specific distributions. And that's the main reason why we went with this. Genetic algorithms and other higher, more complex optimization techniques tend to be more, you can build in more perturbations too. So this is one way to do it. And the interesting thing here is the simple algorithm, just removal and insertion, for most cases has given us very fast convergence to low energy structures. So I think it's more about the simplicity and the historical context with which Monte Carlo has been developed. That's what is appealing for us here.
Thank you. So there's another question from Edwin Joseph. So I will unmute him so that he can ask the question.
Can you hear me?
Yeah.
Yes.
Yeah. So how efficient are the for example SOAP descriptors when we use those descriptors to actually predict the grain boundary lowest energy of specific grain boundary systems?
Yeah, good, interesting question. I actually have a colleague who worked closely with using SOAP descriptors. for not generating the structures, but more to estimating properties. And I think that's where I see more of a utility of using some of these descriptors to maybe estimate not just the energy, but let's say mobility or some other property of a grain boundary. We did try actually to estimate which positions to insert atoms in using some of the SOAP descriptors, and finally what we realized is actually the volume of this tetrahedron or the Voronoi volume is a good enough descriptor for inserting atoms. So really, I think the answer to your question is, what are you trying to do? In the specific algorithm, we didn't find it to be that useful, but like I mentioned, and if you're interested, please feel free to email me. I can send you some papers on using SOAP descriptors for predicting interface properties. There is some very interesting literature there.
I have one more question. When we have systems that are charged, when we have systems like, so in the
Yeah.
grain boundaries, there will always be uh, a net charge on the whole system. So, how does that affect the uh, energy? Can you comment on something? How does that affect the energy of the grain boundary? And what
Yes,
type?
yes. Yeah, excellent question. And maybe one of the reasons why I didn't move, into ceramic systems for this algorithm. You have to take care, you have to be careful how you're, basically what are the boundary conditions to make sure, what is the, what do you call the space charge region is at the grain boundary. It's usually affected by the boundary conditions. For example, what are the chemical potentials that of these individual ions are. But to capture the space charge region, you need a much larger system. And you can use a technique like this using swapping and inserting and removal, but you have to be very careful to make sure that your chemical potentials, again, going back to this idea of a grand canonical ensemble, let's say, is constant during your simulations, right? So again, it can be done in a Monte Carlo setting. We haven't done that yet, and maybe that's a good research topic to pursue as well.
Thank you, sir, for the answers.
Thank you. George has a question. I'll just unmute George.
No, sir. Already I asked it.
Oh, okay. All right. All right. So maybe we can take another, maybe there's two more questions. So what kinds of data structures are efficient for working with atoms, especially in the context of grain boundaries, symmetries, point, pattern matching, and so on?
What kind of data structures? I'm not sure I completely understand the intention of the question.
Okay.
I think we just to maybe provide the context here, we use LAMPS, which is a pretty standard atomistic simulation software, and most of our codes are built to create inputs for that. And another point I just want to make, this field itself is not necessarily a big data problem yet, because we do need these algorithms for getting those big data, right? So maybe once we become a big data regime, that might be a more relevant question.
Sure. Thank you. So Vishal Subramaniam says, thanks for the wonderful talk. Can you please comment on the effects of compositional variation across the grain boundary from the perspective of increased computational complexity and physical relevance?
Yes, yes. So I don't think I have the additional slide here. So we extended partially this to silicon carbide systems. It's a two-component system, but it's very still, restricted by the coordination number there. But if you have, let's say, an alloy system, definitely, again, I think this goes back to one of the questions in the ceramics too. Depending upon how spread out the variation in the composition might be, one might have to go to a larger system. But generally speaking, especially my interest in some of the more interesting topics here, which have to do with nanocrystalline alloy systems. Let's say segregation tends to be very focused or limited to the grain boundary, or maybe a few widths of the grain boundary. So we can get away with it. I do know of some systems where the segregation profile can be very diffuse, and you will need larger system sizes. And atomistic simulations, you can go, what I've showed here examples are thousands of atoms. You can easily go to hundreds of thousands of atoms without it being too computationally expensive. Of course, if you go to millions, then yeah, there is some computational expense there.
Thank you very much. I think the last question is by Anand. He wants to ask a question. So, Anand, can you go ahead? Yeah.
Yeah, Srikanth, excellent talk. I have two questions. I'll try to keep it simple. First one is, I'm curious about the fact that you mentioned only in low symmetry crystals, you have difficulty matching the atoms. So you have a near CSL. Why is that? I mean, low symmetry also has a good CSL structure, right? What's special about low symmetry crystals that gets there?
Right. Good question. So low symmetry systems, let's not even go that low, let's say hexagonal. There are CSL relationships that are perfect matching, but there are also, if you're aware of this terminology, there's like common CSL and specific CSL. So it depends upon the CSL number. If you're going to higher order CSL, then you do get cases where the matching is not perfect and you have to apply distortions. And that depends actually on the C/A ratio in the hexagonal system. So if I'm changing the material system, a CSL that's a perfect match in, let's say, magnesium is not a perfect match anymore in titanium. So you do have to tailor it in some sense to the specific C/A ratio. And there are papers that have tabulated specific to, this is a C/A ratio, then these are the sigmas that you observe, and this is the amount of distortion that you might have to apply to get some other sigmas. So, for specific cases, these have been enumerated. The goal here is, can we generate a general automated algorithm?
And you can actually use even for cubic materials the same system, same algorithm. Let's say if I want copper, I want sigma phi, but maybe a slight deviation from sigma phi, 0.1 degrees from perfect match.
Right. I'm trying to make sure I understand your question here. If I'm trying to move away, so in cubic systems, you will. Oh, okay. I think I might understand your question here. So if you, actually, that's a good question. So you might have, if I slightly move away from sigma 5, then I don't have the perfect match anymore. But if I can distort it slightly, I might get a good match again. Actually, I didn't think about that very carefully, but I think yes.
I'll tell you the context, because we are actually trying to simulate this near sigma boundaries using continuum scale discrete dislocations. And we're trying to match the energy profiles from experiments. And most of these energy of experiments, if you go back to old Sutton-Baluffi experiments, they are actually, the CSL itself, they don't have the energy value, but the near CSL, they have a whole bunch of values at varying degrees from that. So that's why I'm curious. So in principle, we can use your algorithm to generate atomic configurations with near CSL with precise, say, 0.5 degree deviation insert.
Right. I think we can, maybe I will hedge a little bit here. We can go arbitrarily close to something. Can we go exactly? So it has to do with periodicity, setting up periodicity. Then that's where it gets a little complex here. So if I have this, orientation relationship that's in some sense irrational, let's say, and I'm not able to set up a periodic boundary condition, I will not be able to simulate that in this framework. But I can go arbitrarily close to that because I can distort it slightly and then get, and energy is a continuous property, so we can go arbitrarily close to a specific configuration that you're interested in, let's suppose.
Okay. And I'll just, final question from my side. I know it's very long, but is there a good way or something that you have been thinking about on how to sample the grain boundary space let's say we fix the grain boundary normal. Okay, I'm talking from a mechanics perspective. Let's say I'm only interested in grain boundaries. All the normals are same, but I want to sample the entire grain boundary space. Is there a way to do it?
Yeah. Again, very good question, and the student actually working on this tried a few things. So the simple answer is the reason we are developing this kernel is to do that. So there are these Bayesian type techniques that one can use depending upon the property of interest. And we were interested in this cleavage fracture, and I wanted to identify very quickly in this 5-dimensional space where I can get high cleavage energy grain boundaries. One complexity that we ran into very quickly is we didn't have a good kernel that obeys the symmetries, and that's kind of the starting point to that research. And we are at a point where we are now able to define these kernels. So basically, if I have a way to interpolate property on the space, then I can use that as an estimate to iteratively sample the space. So these kernels help that way. Is that a...
Let me pose an inverse problem. So, for example, you have already identified a misorientation space for a particular cubic symmetry, let's say.
Okay.
So you have the Frank-Rodriguez space.
Yeah.
And then we, in principle, sample that space uniformly, just as a misorientation vectors, right? So, but then how do we construct the grain boundaries out of it? So we have the misorientation vectors, which are sampled uniformly, but then how do we construct the grain boundaries to do our property calculations?
Oh, yeah. I mean, if you have the misorientations and the boundary plane normals, this framework is supposed to be doing that. So maybe I might be missing the complexity there, but I also understand, it's not that simple as saying, okay, this is a misorientation, this is the normal, get the structure. But if you have identified those, I think in theory, this framework is built for that. And we have actually, again, you're constraining the boundary plane. We in this project, we have identified about 60,000 grain boundaries that we can simulate in a reasonable computational amount of time. But again, we don't want to simulate all of them, so we are iteratively sampling in those 60,000. So I think we can go pretty high. It does depend a little bit upon how, let's say your HKL indices are very large, right? Which is like a low symmetry plane itself. Then the computational box sizes start to become larger and larger. So, we have to be a little careful there. But again, if you're interested in like a uniform sampling of misorientation, but I want to know if I can go slightly move it so that I get a much smaller box, we can do that too.
Okay. Fantastic. Thank you. Thank you very much.
Okay. Yeah. Thank you. Excellent questions. I'm really enjoying this session.
I'm glad you did. So Narasimhan, I'm done.
Thank you very much. Thanks a lot for the wonderful talk. So this was really great. So let's thank the speaker once again.
Okay.
So
let me stop sharing here. Yep.
How do we, Anand, how do we go from here? We just conclude the sessions.